you very much, and thank you all for continuing on this heliophysics adventure with us. So I want to first of all acknowledge the number of people that have been involved in getting this mission to the point where it is. Harlan Spence is the PI at UNH. We go with our scientists all the way from Alexandrova and Arzamovsky to Zweibel and Zank. So we have a wide swath of the science community, all focusing on trying to understand the nature of turbulence. Now, normally, if the different group of people, I would be telling you all why turbulence is important. But if you're in this room, you probably don't need to be convinced of that. And instead, I need to tell you about why we want to measure turbulence in the heliosphere and how we've done that thus far and what advances need to be made. Right? Is the volume right here? Great. What advances need to be made? So here is the what we call the heliophysics fleet chart. So these are all the current missions that NASA has thrown into the great expanse. The mission that Trevor and Anna were talking about earlier, Parker going and touching, in scare quotes, the corona. Helios is not on here because it was a German-US collaboration launched in the 70s, but it went to kind of similar distances. Because this is a cartoon and probably not that useful for all of you who want the actual quantitative information, TROBE is going incredibly close to the sun. The x-axis here is the distance from the sun in AU, logarithmically spaced. Most of the things that we've thrown up sit relatively close to the Earth, either going in and out of the magnetosphere, going out maybe to the Lagrange 1 point so that you can have that nice gravitational balance and just sit there for decades and measure the solar wind. But the difficulty with almost all of these missions is that there's one of them. And if there's just one of them, you're really only going to be capturing structure that's being advected past you, and only under the assumption that you can get some way of transforming that time series into a spatial series. And so that's the approximation that Trevor was talking about. Here's the fourth version of that Chiani plot. We have a theme going through our talks, where you have a measurement of the power spectral density, nanotesla squared per hertz, as a function of hertz. You see the slopes that you all in this room have come to expect, energy being injected in, cascaded down, and eventually removed by some dissipation mechanism that Greg will start talking about in 25 minutes. But this is a frequency spectra, and what if we want to know about this spatial structure? Well, you can use Taylor's hypothesis, and assuming that everything is flowing sufficiently fast, you can treat your time series as a measurement of the spatial structure. But you're only going to sample along scales that are parallel to what's being advected past you. One spacecraft is what you can do. You can launch more than one spacecraft, though, given enough time, money, and effort. And we've done that in the past. Missions like MMS, multi-scale magnetosphere mission, as well as cluster, have launched 4 spacecraft. And they've been very specifically focused on studying single scales at a single time. Their trajectories have been designed so they form these nice tetrahedra that have separations that are about the order of the electron kinetic scales or the ion kinetic scales, or at other times in clusters missions going up to the MHD scales. But what we really want to do, if we want to understand this multi-scale disorder, is we need an observatory that captures all of these scales simultaneously. And that's what we're going to do with Helioswarm. We're not going to focus on a single scale or even a single point, but rather an observatory made of 9 different spacecraft that will have separations that are as large as the MHD scales in solar wind and down to and through the ion kinetic scales. And so that's what we're going to be doing. Just as a point of history, they convened a group of mostly theorists that said generally N3 is always going to be better than N equals 2, and N equals 4 is even better when we're talking about the number of spacecraft. And my favorite line in this little report by David Montgomery and others is the point at which increasing N by 1 is not desirable is largely determined by economic considerations. So we went through a lot of effort of determining how many spacecraft do we really need in order to capture this full multi-scale process and balance that against economic and engineering considerations. and found that 9 was the number. It lets us capture the large MHD scales as well as the small ion scales at the same time, and this is the trajectory that we're going to be going with. So just to orient you with this probably too busy of a plot, what we have is the actual observatory itself is this pentagon out there. The moon is this open circle there to give you some understanding of where you are in the system. And these 3 different colors are the different kinds of solar wind that we're going to be observing. The red is the pristine solar wind, the stuff that's been accelerated off the sun's surface and hasn't been impacted by by our magnetosphere yet. Stuff that's been shocked, that's been processed by the magnetosphere. And this green stuff is where you have some sort of magnetic connection, some foreshock waves traveling up and actively driving the turbulence then. So in a single year, we're going to get measurements in all these different kinds of environments, both strongly driven as well as turbulence that's decayed as it's come towards us. Now, all of the spacecraft are effectively that same position, but if you zoom in on that particular point, you'll get something that looks like this relative distance plot. So the x and y axes are just the distances in kilometers between this central spacecraft. We have a single hub that's going to deliver all the spacecraft to this place, and then the nodes will be launched off basically pairwise until you form this nice ballet of an observatory where you have some of the nodes that remain incredibly close to the hub, and then some that will go thousands of kilometers apart. So we're currently in phase B, the engineering and technical developments. We'll keep moving towards our different key decision points over the next several years with a launch readiness date, fingers crossed, in 29. So we're not just going to fly spacecraft with nothing on them. We're actually going to measure something. So what are the quantities that we need to actually measure? Well, based on our understanding of turbulence, we want to be able to actually measure those Alsacer variables, right? That nice equation that, that dictates how energy is going to be moved through, both through an advection as well as that nonlinear interaction. In order to do that, we need to measure V, we need to measure N, we need to measure B. And so on all 9 of the spacecraft, we're going to have a measurement by 2 different kinds of magnetometers. We need both of them so we get a nice frequency resolution both at the MHD and at the ion kinetic scales. So these are being built based on magnetometers that are currently flying on both Solar Orbiter and JUICE. And then the Faraday cup is how we're going to measure the ion density, velocity, and radial temperature at a sufficient cadence for us to be able to actually see ion scale structures advecting past the observatory. That's going to be using a Faraday cup that's effectively an improved, or at least a very similar version to the one that's currently flying on Parker Solar Probe and living on a number of the other spacecraft that are currently out in our heliosphere. On the central spacecraft, the hub, we're also going to have an ion velocity distribution measurement made by an ion electrostatic analyzer that will produce those kinds of velocity distribution functions that Mihailo and Trevor were showing, so we can understand how you have non-gyrotropic pressures, how you have anisotropies evolving in these systems, and how that interacts with the turbulence at these ion scales. We're also having a team at UCB build an electron instrument as a student collaboration option, so we can both measure the electrons and train the next generation of people to build spacecraft instrumentation. What dictates these spacings? Why do we need to actually have this particular configuration? Well, we need to make sure that we capture both that break in the spectra, right? The transition between the ion, from the MHD down to the ion scales. And we have been sending spacecraft into the solar wind for decades now, which means we have a good sense of what physical scale that break is at. It's about 1,200 kilometers or so. And so we need to make sure that we're encompassing that scale. We also know what the ion kinetic scales, your gyroscale, your inertial length are. That's all sitting around 100 kilometers or so. These are the probability distribution functions extracted from a quarter century of wind observations. You turn that into a 2D histogram, and you make sure that most of that time we're going to be encompassing both of those scales with the scales covered by our observatory. So that's the spatial scales. We also have a requirement that we are measuring quickly enough that we can measure those advected scales that are going to be pushing past us. And given the kind of hundreds of kilometers a second that we typically measure, that dictates that we need to be measuring at, 8 times a second to make sure that we're actually resolving these structures moving past us in typical solar wind conditions. Now, and we're running a bit short on time, so the thing that I wanted to point out on this slide was the solar wind is a wonderful natural plasma observatory. Unlike a simulation, you can't dial in and say, I want beta of 100 and anisotropy starting out to be 2, but you can wait long enough and say, what will beta be, and start doing statistical analyses where you have something that is relatively high cross helicity or relatively low beta. And so we can look again to see in the different environments we're going to be sampling, the pristine solar wind, the magnetosheath, we're going to have relatively lower and relatively higher beta intervals that we'll have to be able to look at different kinds of turbulence that are hopefully going to be applicable to many of those more distant objects that you all care about and hopefully probably won't be able to send a spacecraft to in the lifetime of anyone in this room. So what are the shapes that we actually need? We don't want to just throw these spacecraft out there. We want to make sure that they actually are in a configuration that will enable us to do the kinds of analyses we want to do. We basically want to make sure that we have these nice baseline separations for your 2-point correlations, your n-point correlations, but we also want to make sure that we have these good tetrahedral configurations, right? Someone earlier asked, why haven't you calculated the magnetic curvature from Parker? Well, there's only one spacecraft moving along. It's kind of difficult to get a 3-dimensional gradient with only one spacecraft. If you have these nice tetrahedra, and if you have them at many different scales, you'll be able to look at what the curvature of the magnetic field or any of the other vector fields are as a function of scale. Now, importantly, by choosing 9 of these, we're going to have 36 different baselines between the 9 different configurations, 126 different tetrahedra that you can possibly choose from, and because combinatorics are fun, all the way up to 382 different polyhedra that you can use to assess the gradients of the fields. Now, it's not enough to just hope that all of these are going to be in the right place, but rather we've worked with the flight dynamicists to make sure that the actual positions of these spacecraft are going to be oriented so that all of the baselines are not aligned in a single direction, but rather span both a long transverse and the second transverse direction, the local field and flow directions. So this will allow us to do the kind of 2-point correlations, the cascade rate calculations, the general structure functions that you want. That's the flight dynamicist's way of looking at it. This is the way I try to think about it, where you take those 36 different baselines, you project them into a particular coordinate system, in this case the RT and N direction, and you ask, how many times do you have a separation between 2 spacecraft that's below 100 kilometers in the N direction and in the R direction and in the T direction, and then in the other 2 sides as well, and the number of times that you've basically put a check in all 9 of those boxes, you say that's going to be a good hour for making these kinds of baseline calculations that will encompass all of your scales and all of your directions. We'll get thousands of those hours. Now, similarly, and this allows us to do calculations like the instantaneous, the calculation of both the decorrelation in both time and space. So we're talking about correlation functions. When we're doing that with single spacecraft, you're basically just sampling along this decorrelation, mostly as a function of distance, a little bit as a function of time. But with multiple spacecraft, you really will be able to disentangle that both in time and space. You do want to be able to calculate, I don't know why the movie's not coming up. There we go. You will want to be able to calculate these different tetrahedra as well. We already talked about why we want to be able to do that, right? You want to look at those, the magnetic field curvature. You want to look at other applications like the wave telescope. We've designed them so that we will have good planarity and elongation. You're not going to be incredibly elongated so that you're effectively a pancake or a sausage, because that's not going to be particularly useful for your analysis for the different kinds of gradient applications. So we want to make sure that we have good polyhedra that are down in this pseudo-spherical space. And importantly, we want to make sure that we have very small ones and very large ones, because whatever gradient calculations that you're doing are going to be most sensitive to structures that are of the same order as your configuration. And so that's what this color is indicating for this case. We have the same kind of movie where we say, yes, how many pseudospheres? I guess we probably should have labeled that meatball, but you know, it falls apart at a certain point in time. So we want to make sure that we have intervals, that you have both this really small tetrahedra, this little blue guy right there, as well as some of the larger ones that are all filling this space simultaneously, so that you can capture those changes in the background fields. So do this well, we can do different kinds of magnetic field reconstructions. If I were faster on my feet from earlier today, I would have put in some analyses of magnetic gradients, or the types of things that you can do here. This is great work that my grad student, Teddy Baranen, has been doing, looking at different ways that you can reconstruct the full magnetic field from just these 9 different time series that are flying through it. Both the kind of simple, well, if you have a gradient of the magnetic field, just do a Taylor expansion of that, and then perhaps do Taylor expansions from different subsets of the spacecraft and add them together in a statistically weighted way. But you also can do radial basis functions or other kinds of inverse weightings that actually he's showing preserve many of the properties of the turbulence that we care about, things like intermittency rather than just the overall general structure. So as I said, we're going to have thousands of hours in these different regions, these different kinds of turbulence in these different configurations. But importantly, we're not going to be selecting just a particular subset of these intervals to bring down. Every science measurement is going to be measured and then relayed back to Earth, so that if any of you care about a particular kind of plasma environment, care about a particular kind of interval, and one of the spacecraft wasn't in exactly the right place to satisfy these hours, that data is still going to be down on Earth for you all to be working with. So I think I'm going to leave it there. I may have rushed a little fast, but hopefully left time for questions for you all. This is how we're actually going to deploy. It's a nice little video where the hub is out there, the first 2 nodes are kicked off, and then 14 days later, the next 2 come off in a pairwise fashion, and we build this up over those first few months. We then calibrate everything, make sure everyone knows where the other spacecraft are, and then we will be off to the races. So as I said, this is current launch readiness date is 2029, and we're quite excited for what we're going to be able to do with these local measurements of plasma that help us understand plasma turbulence, both in our heliosphere and throughout the universe. We have a full mission overview, I think it's the left one, as well as a connection to the website providing some more details. So with that, I'd love to take any questions you have.
All right, thank you, thank you. Does anybody have any questions? Okay, just a lot of flight dynamics, yeah. Yeah, still, wow.
The hypnotism is intentional.
Okay, Sasha, go ahead.
So this was spectacular. Thank you. The movies and animations are helping us to visualize and eat the popcorn really quickly. I'm wondering, when you showed the sort of edge-on view of the orbits.
Yeah.
So here it looks everything is up-down symmetric, right? The satellite goes up, and there's another one that goes down. Mm-hmm. I would imagine if I look at sort of like if I take a long exposure of this, I would have up-down symmetry as well. But I think in the slide where you were showing that, it looked like they were mostly pointing downwards. So I'm curious, how the bottom right panel, or am I misreading this?
So no, you are correctly reading this. So notice these are in RE, and this is in kilometers relative to the hub. So the hub, in order to get into this particular orbit, goes through a lunar swing by and goes into this place where it's actually going to dip almost 10 Earth radii down and then swing back up. And so we're not perfectly in the equatorial plane. We're dipping down for an extended part of our apogees. But then the symmetries are preserved with respect to the hub.
Gotcha. Thank you.
Certainly.
So I have a more pessimistic question. Satellites fail
Yes.
fairly regularly. So,
Yeah.
you know, have you analyzed, you know, what's the worst case failure, and have you tried to do backups?
Yes, we have. Yes, we have. So we will be able to complete the science with 7 of these spacecraft. And so we have plans for how to handle if one spacecraft fails, if the Faraday cup stops working, but the magnetometers keep working, right? And part of that will be accounting for the number of hours that we've already accumulated in this configuration or that configuration or this kind of solar wind or that. In fact, we're already going through those exercises. On I think Monday, we're going to have a mock anomaly review board where they will throw at us, you know, this one has failed, what are you going to do?
Okay, go ahead.
Thanks for this nice talk. I just had a question. So am I understanding this correctly? You can construct the magnetic field gradient tensor on a plane? Is that correct? Like you can get the magnetic field gradients on a plane? So you can construct a whole tensor?
With
Just feels asked with the magnetic field reconstruction.
I hadn't gone to, so for the reconstruction, for the particular methods we've been focusing on, we've not gone to the second order. Oh, no, sorry, actually that's not true. In Buranin 21, we did a second order reconstruction, which does require that tensor calculation. The difficulty is the method we implemented as well was only accurate over a very small region near the barycenter of the overall configuration.
I see.
And the first order gave us a broader, accurate representation over a wide volume. But I would need to think about ways of maybe trying to get that second order tensor over larger volumes. It's definitely something that should be extractable.
That would be really cool because then you can, you know, almost get at the O points and the X points from the magnetic field gradient tensor.
So I think we should be able to get at O points and X points from just the structure of the gradients here, right? People have been working on doing that with just 4 spacecraft.
Yep.
So with 9, that should definitely be within our wheelhouse.
Awesome, that's exciting.
Yeah.
Okay, does anybody else have any questions? All right, well, great. Okay, so the next thing, while we get set up here. Yes, thank you.